In the early days of aviation, the only form of aircraft brakes was the tail skid. Though primitive in design, it was an effective means of braking. As the airplane touched down at very low speeds, the skid dug into the dirt, resulting in a very short landing road. As runways became paved, tail skids gave way to tail wheels with brakes installed in the main wheels. And with only a few thousand pounds of weight to stop, the pilot could feel when the aircraft tire began to go into a skid and react accordingly. Today's modern jet aircraft present a new problem for effective aircraft braking in all weather conditions. These aircraft touch down at high speeds on small diameter tires inflated with very high pressure. This only allows a small contact area with the runway surface, and coupled with the fact that many of these high-speed jets use a multiple of wheels, the pilot is often unable to feel an individual condition of the wheels as he applies braking pressure. Now, to overcome this problem, modern aircraft technology has developed a modulated anti-skid braking system to allow maximum braking no matter the weather, without the danger of flat spotting or blowing tires from a locked wheel condition due to an actual skid. To learn more about this new technology in aircraft braking, the Aircraft Wheel and Brake Division of the Goodyear Aerospace Corporation presents this training program on typical aircraft anti-skid braking systems to help you, the professional aviation maintenance technician, better understand these vitally important systems. When an airplane touches down on the runway, it possesses a tremendous amount of energy because of its weight and velocity. And before the airplane can be brought to a stop, this kinetic energy must be transformed into brake heat and other drag forces. To stop the airplane, the pilot applies the necessary braking force, which slows the wheel's peripheral speed below that of the airplane, causing the tires to grip the runway surface, slipping slightly, but producing a great deal of tire drag. Now, as long as the tire is slipping on the runway surface, it provides an effective stopping force. And as this slip increases, the stopping force becomes greater, but only up to a certain point. As soon as slippage becomes excessive, the braking force decreases rapidly, and a true skid condition develops. Now, at this point, it is only seconds before the tires wear through, blow out, and control of the airplane can be lost. To understand how an anti-skid braking system works, let's look at an aircraft without an anti-skid system. Here, when the pilot applies the brakes, the brake pressure rises and the wheel decelerates enough to cause the tire to slip. If this braking pressure is held, this slip will continue to increase, reducing the tire and runway friction rapidly, causing the wheel to lock up. If this continues for more than a few seconds, the tire will wear through and blow out. Without an anti-skid braking system, the pilot can usually detect a skid condition. But by the time he releases the brakes, a certain amount of time will lapse before the wheel spins up and he applies the brakes again. Now, this method uses more runway length and time to stop. From here, let's examine early anti-skid systems which were developed to automatically sense wheel deceleration, wheel lockup, and the rate of wheel speed recovery. In these early systems, the brakes could be automatically applied or released, but the slow response of the early skid control valves caused brake pressure to often go above the skid threshold before it was released or dumped. As a result, these systems were often ineffective and even caused the skid to be more pronounced. thus requiring more time for recovery. The modern type of modulated braking system overcomes these problems by allowing brake pressure to increase until it reaches the skid threshold, then cycles the pressure with small excursions to hold the wheel at the skid threshold for maximum tire drag. The heart of this system is the control box, containing electronic skid control and modulator circuits. Now, these circuits monitor the wheel speed signal and control the brake pressure automatically. The special anti-skid valve used in this new generation of anti-skid braking systems is an extremely fast-acting electro-hydraulic servo valve, which regulates.
That contains the torque motor up at the top.
This is achieved by a continuous command from the control circuitry. By rapidly releasing and applying a controlled amount of pressure above the nominal skid pressure level, the wheel speed is held in the critical slip area, permitting the plane to be stopped in the shortest distance possible without the danger of flat spotting or blowing the tires. Another feature of modern anti-skid braking system is that when the wheel rotation is below approximately 10 miles per hour, the anti-skid system is inoperative, allowing full braking control by the pilot for taxiing. During this condition, the wheels may lock up, but at this speed, tire damage will not result, and the danger of the pilot losing control is negligible. Well, now that we are familiar with how a modern anti-skid braking system works, let's review the components involved, how they operate, and basic troubleshooting procedures. There are three basic components of an anti-skid system: the hydraulic valve, a control box, and a wheel speed sensor. The anti-skid valve consists of a torque motor which receives signals from the control box. Here, a spool-type valve directs hydraulic fluid pressure from the pilot's brake control valve to the brake, or from the brake to the system return manifold. The anti-skid valve is located in the line between the pilot's brake control valve and the brake. When the anti-skid system is off, or when the wheel speed is below approximately 10 miles per hour, or a normal no-skid operation exists, this valve is passive, which means the brake pressure is directed to the brakes and the valve has no effect on the system. But when a skid does occur, let's say on the left wheel, the left anti-skid valve will dump the pressure from that brake back into the system return manifold until the left wheel starts to spin back up. Then the pressure will be automatically applied again. This action is independent of the brake control valve operated by the pilot, and the brake pedals can be fully depressed all of this time. When the brakes are applied by the pilot and no skid is produced, the anti-skid control box does not activate the torque motor coil in the anti-skid valve, and a flapper, centered between two nozzles in this unit, maintains equal pressure on both ends of the spool valve. Now, this causes the fluid from the brake control valve to go directly to the brakes. But when the torque motor receives a signal from the anti-skid control box that a skid is developing, this flapper moves over, restricting one of the nozzles and opening the other, to unbalance pressure on the lands in the spool, moving the spool over. By doing this, the pressure port is sealed off and the brake port is connected with the return port, dumping brake pressure. The extreme sensitivity and rapid action of this type of valve modulates the pressure to the brake, applying only enough pressure to hold the wheel in the critical slip area. The next component in a modern anti-skid braking system is the wheel speed sensor. of which there are two types, AC and DC. The AC transducer is a variable reluctance frequency generator, which uses an exciter ring to generate an AC signal. This frequency varies according to the wheel speed and is fed into the main control box, where a converter circuit changes the varying frequency into a direct current signal that is proportionate to the wheel speed. With a DC type of sensor, the signal is developed by means of a small permanent magnet tachometer generator located in the wheel axle. Here, linear voltage is developed proportionate to the wheel speed. For example, 1/10 of a volt generated equals approximately 1 mile per hour rotation speed. This compact DC wheel speed sensor is mounted in the axle of the aircraft landing gear, where a special blade attached to its shaft is driven by the slotted drive tube installed in the wheel hubcap. Many of the anti-skid systems employed in today's corporate aircraft utilize the DC tachometer generator system. To understand how this type of system operates, let's analyze the various components during a typical landing. The control box, features, and functions will be discussed as a part of this analysis. Here, prior to touchdown, 0 voltage is indicated from the wheel speed sensor. This signals the locked wheel detector circuit located in the control box to hold the control valve open to the system return, and this prevents pressure being applied to the brakes. As soon as the airplane touches down and the wheel spins up, the speed sensor immediately produces a voltage, which is sent to the skid detector and locked wheel arming circuits in the control box. Now this releases the control valve, allowing pressure applied by the pilot to go directly to the brakes. As the brake pressure increases to the skid level, the wheel decelerates until the tire reaches its critical slip condition and begins to skid. When the wheel deceleration exceeds a threshold level, the skid detector circuit in the control box sends a signal to the anti-skid control valve to reduce pressure to the brake. Now, at the same time, this signal is passed to the modulator in the control box, which acts as a memory circuit to hold the average brake pressure near the skid level. As soon as the wheel stops decelerating and starts to spin back up, a signal from the control box automatically causes the control valve to reapply pressure to the brake, but only long enough for the wheel to again reach its skid threshold. As long as the brake pedal is depressed, calling for full braking, the control box will provide these signals at a high rate of speed to alternately apply and release the brakes, holding the wheel in the optimum slip area. As soon as the wheel speed is down to about 10 miles per hour, the anti-skid system will automatically deactivate, giving the pilot full braking control for taxiing. Any anti-skid system should be simple to operate, and provision should be made to ensure proper operation under all weather and runway conditions. If the speed of one of the wheels drops below approximately 10 miles per hour, while any other wheel is turning more than approximately 20 miles per hour, as will happen if the wheel hydroplanes on a wet runway, the locked wheel detector circuit will automatically dump the pressure to that brake and hold it dumped until its speed builds back up above 10 miles per hour. A squat switch on the landing gear will hold the locked wheel arming circuit energized before landing, so the locked wheel detector will hold the control valve in a dumped position, so the brakes cannot be inadvertently applied before touchdown. But when the wheel spins up on touchdown, the voltage generated by the wheel speed sensor will override the squat switch, and the brakes may be applied even before the full weight of the airplane is on the struts. A warning light may also be incorporated into the circuit to indicate to the pilot any time the anti-skid system is not operational. Now, this allows the pilot to plan his landing and apply the brakes accordingly, minimizing the danger of skidding. The anti-skid test system will vary with the different aircraft. For example, on the Falcon 20, when the airplane is on the ground and 700 pounds per square inch of pressure is applied to the brakes, the test light will illuminate. And when the anti-skid test switch is depressed, a simulated spin-up signal is sent into the system, testing the electrical and electronic integrity of the entire circuit, including the speed sensor. Now, if all the circuits are working properly, the test light will stay on as long as the switch is depressed. But when the switch is released, a simulated lockup signal is injected into the circuit, which will momentarily lower the pressure to the brakes. And the test light will go out and come back on in a few seconds. When the airplane is in the air, the squat switch on the landing gear changes the system test logic. The pilot must apply greater than 700 pounds per square inch braking pressure to actuate the pressure switch in the line. Now, this pressure will not be applied to the brakes until the test switch is actuated. By doing this, the test light will illuminate. Releasing the test switch will cause the brakes to release, and it is in this position the test light will automatically turn off. By depressing the test switch, a wheel speed signal is injected into the control box. This causes the light to turn on, signifying that the system is fully operative. If the test lights do not go on, this indicates there is a malfunction in the anti-skid system, and the pilot is alerted to the absence of anti-skid protection. Other than this, braking action will be normal, and he can turn the anti-skid power system off to avoid asymmetrical braking. In the event of a system malfunction, troubleshooting may be performed by a professional aviation technician in the field to return an airplane to service in a short amount of time. In order to do this, first check the units that are most accessible. For example, in the Falcon 20 anti-skid system, we should begin troubleshooting with the wheel speed sensors. Here, a tweak test may be employed to check the entire system for operation. With the hubcap removed and pressure applied to the brakes, spin the sensor blade in the direction of wheel rotation with your fingers. You'll only get about half a revolution, but it is the rate at which it is spun and stops that's important. If the system is operating properly, the brakes will momentarily release and reapply. This may be seen by watching the discs. If the brakes do not release when the speed sensor is tweaked, it is possible that the generator is defective. Now, this may be further checked by removing the connector from the back of the wheel speed sensor and checking the resistance of the armature as the blade is rotated. In this test, use an accurate ohm meter and measure the resistance as the blade is slowly rotated through 180 degrees. The resistance should be between 250 and 375 ohms. Also, check the polarity of the sensor by setting the multimeter to the lowest DC voltage scale and holding the positive lead on pin B and the negative lead on pin A. When the blade is tweaked in a clockwise direction is viewed from its drive end, the meter should read upscale. If the wheel speed sensor checks out all right, replace and safety the connector plug and carefully reinstall the hubcap. Be sure the drive tube is not loose and it fits properly over the blade of the sensor, and the alignment rivet fits in the hole in the wheel. Finally, be sure there are no dents in the cap. The next logical step in troubleshooting is to check the control box. Assuming there is an indication that the left anti-skid system is inoperative, remove the two plugs from the anti-skid control box and reverse them. If the malfunction indication stays on the left, in all probability the trouble is not in the control box. But if the malfunction changes to the right side, the control box is defective and should be replaced. Here's a warning. After connectors have been swapped, be sure that they are placed back on the correct receptacle.
No kidding, huh?
The only other component in the anti-skid system left to test is the control valve itself. Since this is an electro-hydraulic device, the problem could be either electrical or hydraulic. To check the electrical integrity of the control valve, an ohm meter reading of 500 ohms should be indicated between pins A and C. If regular braking is normal, but the brakes will not release when the speed sensor is tweaked and after testing the wheel speed sensor, control box, and the coil of the control valve, the most probable cause of trouble is in the control valve, and it should be replaced. The most probable cause for control valve failure is fluid contamination. For this reason, valve manufacturers have made provisions for reducing this malfunction. Typically, a 15-micron steel mesh filter is installed in the valve, and it may be replaced by the manufacturer or his authorized service facility in the event of valve failure. These valves may leak between the manifold and valve assembly. This joint is sealed with special O-rings, which may be replaced in the field after the valve has been removed and taken into a contamination-free work area. Caution: before attempting any repair to the valve, be sure to check with the manufacturer to ensure that you have the latest service manuals. Modern anti-skid systems are a vital part of the aircraft braking system. For this reason, during any troubleshooting procedure, be sure to check the entire system for malfunctions. Be sure there is no air in the system and that the fluid to the brakes is perfectly clean. Air, for example, will cause spongy braking action and reduce anti-skid performance. And contaminated fluid can cause the brakes to drag. Misadjustment power brake valves can hold pressure in the system, so the brakes will not fully release. Keep in mind, this program has used the Falcon 20 anti-skid system as a typical example. While other general aviation anti-skid systems operate in a similar manner, there are differences in each system, such as single and paired wheel control, inboard and outboard wheel control, different types of test logic circuitry, plus other features. So be sure to consult the manufacturer's service manual for specific operating information. An accurate knowledge of the operation of any anti-skid braking system gives us the ability to recognize problems before they become serious, to correct them, and return the airplane to service in the shortest amount of time possible. For this reason, it is hoped that this program has helped you to understand more fully this important system on our modern high-speed aircraft. For further information regarding these and other systems, write Goodyear Aerospace Corporation, Aircraft Wheel and Brake Division, 1210 Ascalon Road, Akron, Ohio, 44315.
Okay, so you saw a little bit about what they use in that circuit for anti-skid. There's three major components. It's electrohydraulic. You've got one electrical component that's got a wheel speed sensor. It can be either AC or DC. The DC wheel speed sensor is really a generator. It's an electrical generator. So is the AC one. The big difference is the sensors are directionally oriented. You'll notice that when they did the tweak test, they're rotating the blade that's in the wheel speed sensor a certain way. And if it fails the tweak test, they sometimes probe and they look a little bit deeper to see if the wheel speed sensor is at fault in the circuit. The reason that they check an upscale reading with the ohm meter is that there's a potential that somebody has got the wrong wheel speed sensor, or at least reversed the wheel speed sensors from left to right. The pins A and B are relative in nature. So the wheel speed sensors are marked left brake or right system or right side. So if they're misinstalled, obviously the ohm meter reading won't read upscale. The other component in the circuit is going to be a control box that contains the modulating circuit for the input of the wheel speed sensor. There's a lot of things that go on into it, but what it's doing is it's actually timing the drop in voltage that's sensed by the wheel speed sensor in order to detect a skid. And I don't know if I got this right, but it might be a tenth of a volt for 1 mile per hour, a tenth of a volt for 10. What that wheel speed box is doing, in that control box, it's sensing the drop in voltage that occurs as a result of a skid. If the threshold, or if it's too great, it senses, or at least it provides a signal to the control valve, which will in turn dump brake pressure and sends it back to the reservoir. So regardless if the pilot has got his foot on the brake pedal, it doesn't make any difference. The fluid momentarily is being returned to the reservoir, and the wheel is allowed to kind of regenerate itself in terms of speed. So again, the object of the game is to keep the wheel in a skid, in a threshold of a slip. If the slip goes on too long, or at least the wheel speed degrades too much, now you're in a skid condition. It's going to take forever for that wheel speed to come back up again.
What is the definition of a slip versus skid? I understand skid, but slip.
Oh, that used to be a secret, that modulator circuit that actually determines when the thing actually trips and goes back to braking. And I was looking for my PowerPoint for when I used to teach the landing gear class. I found out eventually how much of the actual drop in voltage over a period of time is required for it to reestablish braking. But I don't have the PowerPoint available anymore. But it's not just the voltage that's produced. To understand that, what you're doing is the device is actually sensing how fast the voltage is decaying in order to be able to sense when a skid is occurring. The FAA has got a few test questions involving anti-skid systems. And again, what I'd like you to remember is, number one, it's electrohydraulic. Number two, there's three components that are involved. You got a wheel speed sensor, you have a control box, and you've got a control valve. Another thing to kind of remember may be when problems develop in the control valve, it could be either electrical or it could be hydraulic. The electrical portion of the circuit contains the torque motor that's being influenced by the control box. But the problem could also be hydraulic in nature, where you've got the lands of the pilot valve that route hydraulic fluid. You could have debris that's caught in that in order to prevent the spool from moving. So again, just a few different things. That's what I can tell you about these particular circuits. Large aircraft have what they call anti-skid, and they also have auto braking. But or at least for a lot of the corporate aircraft, they don't really have an auto braking circuit. They just have an anti-skid system. And this is really simple. On this, you just had a left and a right main, and one channel of it in that control box went to each of the wheel speed sensors. For a big aircraft, you're going to have to look to see what they do in large aircraft to accommodate that. And again, also in many large aircraft, you'll have an auto brake circuit that provides for automatic braking, not necessarily just anti-skid, but automatic braking control. Okay, so that's what I can kind of tell you. Anything else? I guess what I got for you next, I've got a couple of things that will kind of provide you with an overview of hydraulics. And what do I have for you? How about 757, overview and component location? We'll talk about flight controls maybe next week. And, but I'll kind of give you this. This will provide kind of an overview for a Boeing aircraft anyway, for what they use for the independent systems of the aircraft for hydraulics. The architecture is similar to most Boeing airplanes. And let's see, what do we have? We got a plane.
This program provides an overview of the 757 hydraulic systems and their components. The 757 has 3 independent hydraulic systems. These systems provide power for the operation of flight controls, landing gear, brakes, thrust reversers, and nose wheel steering. The 3 systems are named for their general locations and are color-coded for easy identification of tubing and components. The left system is coded red, the center system blue, and the right system is green. The 3 hydraulic systems are normally powered by a total of 6 pumps, with additional backup pumps located in the center and left systems. 2 engine-driven pumps, or EDPs, and 4 alternating current motor pumps, or ACMPs, provide hydraulic power during normal operation. For backup operation, 2 additional pumps provide power for essential systems. The ram air turbine, or RAT, can pressurize the center system for operation of flight controls. The power transfer unit, or PTU, enables the right hydraulic system pumps to supply left system pressure for landing gear, trailing edge flaps, and leading edge slat operation. The distribution of hydraulic pressure from the 3 hydraulic systems provides adequate flight control operation after failure of 2 systems. If all normal pump operation fails, the ram air turbine can power the center system for operation of flight controls. You will learn more about the specific pumps as we look at each hydraulic system in more detail. Let's begin with the left system. This hydraulic system provides hydraulic pressure to operate flight controls, left engine thrust reverser, flaps and slats, landing gear, nose wheel steering, and alternate brakes. The left hydraulic system is powered by an engine-driven pump, EDP, and the alternating current motor pump, ACMP. For backup operation, a PTU, or power transfer unit, can power the landing gear, flaps, and slats. We will look at the engine-driven pump first. The EDP is a variable displacement pump driven by the engine accessory gearbox and capable of delivering 37 gallons per minute at high engine speeds. The pump is depressurized by energizing a solenoid-operated valve. The EDP filter module is located in the left engine strut fairing. It consists of check valves and pressure and case-drain filters with differential pressure indicators, sometimes referred to as delta P indicators, which indicate a clogged filter. Located on the filter module is the system low pressure indicator switch, EDP low pressure indicator switch, and the EDP overheat temperature indicator switch. Also located in the engine strut fairing is the EDP supply shutoff valve and the pressure and supply ground power connections. Located in the left wheel well, the alternating current motor pump, or ACMP, is a variable displacement electrically driven pump rated at 6 to 7 gallons per minute. Located on the pump is the ACMP overheat indicator switch. The ACMP filter module consists of check valves and pressure and case drain filters with delta P indicators. An ACMP low pressure indicator switch is also located on the filter module. A system pressure relief valve is located outboard of the return filter module. The backup hydraulic pump in the power transfer unit is a fixed displacement pump capable of delivering 22 gallons per minute. Right hydraulic system pressure operates the PTU motor, which drives the PTU pump in the left system. A wear indicator extends when motor wear is beyond limits. The PTU pressure filter module has a check valve, filter, delta P indicator, and 2 pressure switches, one for indication and one for control. The case drain filter module for the PTU has a check valve, bypass valve, filter, and delta P indicator. The reservoir for the hydraulic system is located on the forward wall of the left wheel well. The reservoir has pressure switches, a reservoir depressurization valve, sampling valve, and a sight glass for fluid level indication. Other components include a pressure relief valve, a quantity transmitter, a temperature transmitter, and a drain valve. All 3 reservoirs have the same components and are pressurized by the pneumatic system. A reservoir pressurization module is located on the keel beam forward of the wheel well area. Fluid flows through a heat exchanger located in the left wing and a return filter module before entering the reservoir. The return filter module has both bypass and delta P indicators.
That PTU was a combination of a pump and a motor. So again, it provides for emergency use in a way. So the idea is if you lose pressure, it's using the motor side of the good portion of the other hydraulic system to attempt to draw fluid from below the standpipe of the reservoir of the system that's inoperable. There's no direct transfer of hydraulic fluid. It just attempts to reestablish pressure using reserve fluid in the reservoir.
The heat exchanger is located in the right wing.
In
The
the fuel cell,
PTU control valve provides right system pressure through the keel beam to the PTU motor in the left wheel well. Supply and pressure isolation valves operate together when the reserve brake switch is activated to provide reserve right reservoir fluid to the right ACMP to pressure the brakes only. Right hydraulic system pressure operates an actuator to stow the ram air turbine. The actuator is spring operated to deploy the rat. The third hydraulic system, or center system, provides hydraulic pressure only to the flight controls. The center system is powered by 2 ACMPs located in the left aft body fairing. There is one filter module for both ACMPs. The ACMP filter module has 6 check valves, 2 pressure filters, 2 case drain filters, 4 delta P indicators, and low pressure switches for both ACMPs and the center hydraulic system. The reservoir is smaller than the left and right hydraulic systems, but has the same components. Fluid returns to the reservoir through a heat exchanger in the left wing and a return filter module. The return filter module has check valves, filter, delta P indicator, and the center system pressure relief valve. The ram air turbine, or RAT, is in the right aft body fairing. It has a turbine, gearbox, and an 11-gallon per minute hydraulic pump. An actuator controlled by 2 solenoids deploys the RAT by spring force. A control valve located in the RAT compartment and a safety valve in the right wheel well control right hydraulic system pressure to stow the RAT. A lever on the checkout module is used to back drive the RAT for ground test using center system hydraulics. The module also has check valves, filters, and a pressure switch. A control switch is for ground deployment and stowing of the RAT. Tachometer module lights indicate an on-speed or overspeed condition during ground test. The right system pressure transmitter and shutoff valve are in the right wheel well. The left and center system pressure transmitters and tail flight control shutoff valves are located in the left wheel well. The hydraulic control panel is on the left side of the flight deck overhead panel, or P5. On this panel are the control switches for the left and right engine-driven pumps and the AC motor pumps. These are alternate action lighted push-button switches with a white on indication for switch position, an amber low pressure light for each pump, and an amber overheat light for each pump. Above the pump control switches in each system is an amber reservoir light that shows either reservoir low air pressure or low fluid quantity, a system low or light. A RAT
Trying to fix the tracking of that thing, I noticed it's kind of jumpy.
panel. The RAT can also be automatically deployed when the airplane is in the air. An amber unlock light in the switch illuminates when the RAT is not stowed, and a green pressure light illuminates when the RAT is producing hydraulic pressure. On the right side panel are switches that control the tail flight control shutoff valve in each system. The PTU manual switch is used to manually operate the PTU for testing. The PTU also has control circuits that automatically operate the unit. Engine fire switches located on the control stand control the associated EDP supply shutoff valves and depressurization solenoids. The ICAS displays cautionary and advisory alert messages on the upper display and status or maintenance messages and data on the lower display for the hydraulic systems. The status page displays reservoir fluid quantity and system pressures. The electric hydraulic maintenance page shows system pressure, reservoir air pressure, fluid quantity, and fluid temperature. A reserve brake switch on the main instrument panel turns on the right hydraulic system ACMP and isolates its output to the brake system. This concludes the basic overview and component location of the 757 hydraulic system.
Old, but it's still okay. I think I've got a few animated slides someplace that show you something of what they do on Boeing aircraft for their architecture and hydraulics. See if I can find it for you. Yeah, here we go. You'll notice that what they've done is they use 2 different separate systems to power primary flight control. So they got, in this case, it's a 737 aircraft, but they got a system A and a system B. And through use of different hydraulic systems that are independent of each other. They power most of the primary flight control. So you got aileron and elevator. It looks like it comes from two sources. The rudder also looks like it comes from two sources as well. Some of the components are powered by one circuit normally, but a changeover occurs as a result of using either the usually the power control unit if they have one. So there's a landing gear transfer unit that's their power control part control unit, or if they have the device. They've also got the ram air turbine that's useful too. Usually in many of the Boeing aircraft, the RAT only will supply fluid for flight controls and flight, but sometimes other things as well. So it varies. And another schematic. Oh, notice also too, the heat exchangers. They mentioned in the video that the fluid goes, or the K-string goes back to the reservoir, but that heat exchanger is between the two, so between the pump and the reservoir. And these are located really in the fuel cells of the aircraft, so they're attempting to cool down the fluid prior to getting back into the reservoir. And this is really part of the K-string that comes off of each of the pumps. And let's see, right system. And here's an animated version. I think it shows all of the components operating at the same time. You can see left, center, and right. And the ram air turbine has been stowed in this position. The PTU is non-operational, so it looks like everything is being supplied with fluid. And the left system just in operation. Center system only in operation. It uses, in this case, this uses two ACMPs. I don't think it has any associated engine-driven pump. The left and the right system do. So they've got left and right engine-driven pumps. By the way, the pumps are the same. The only difference is the mechanism used to drive them. So one of them has got a shaft in order to mechanically turn it from the accessory drive. The other one just powered by an AC motor. And here's the right system. And this shows you failure of one system. This would assume that the right system is good and the left system is not operational, at least you don't have enough fluid. So we're drawing fluid really from the bottom of the standpipe in order to make it work. Here's a better picture to kind of show you what's happening. I don't know if I've got that. No, I don't. So the motor side of the circuit is really going to be the right side. And what you're doing is you're using the motor of the PTU in order to drive the pump of the PTU on that side of it to use fluid from the bottom of the reservoir on the left side. There's no direct transfer of fluid from the right system to the left. It's just an attempt of reestablishing pressure by using whatever remaining fluid that you have below the level of the standpipe in order to make it work. So. And that's important. This uses the RAT, and it looks like flight controls primarily. For brakes, I don't know what they're doing for emergency for brakes, but again, maybe they've got that alternate brake deal. But again, this uses the RAT. So they deployed the RAT, and it looks like they're applying fluid under pressure for elevator feel, stabilizer trim, yaw damper, left and right aileron, spoilers, rudder, and elevators. So that would, I guess this would assume almost complete hydraulic failure. And extension and retraction, an alternate extension of the gear. It's kind of interesting to look at the architecture of other aircraft too. Here's one from a Lear 20. And again, it's not as sophisticated, but it's got certainly input from independent hydraulic circuits. You can see what they're doing with flaps, spoilers, reversers, but the flight controls in this aircraft might be purely mechanical. Some, you'd be surprised, the early versions of like the Cessna Citation, the 500, they had all manual flight controls, and there were only maybe 2 or 3 components that were hydraulically powered. The brake system obviously was, but the flight controls were all straight mechanical. No boost for hydraulics. This one, older military aircraft, F-104. again, we can kind of assume what they're doing here. They're using system pressure from a couple of different sources in order to be able to make the primary flight controls operate. Sometimes they'll have independent servo actuators. Sometimes a servo actuator will be a single one, but again, it will have a tandem type of working so that you pretty much provide for separation of hydraulics inside of the actuator. And that's what we've got. We'll cover maybe a little bit of this later toward the end of the class. The Merrifluid Power book covers the distribution of hydraulic fluid from, they've got the power section, which would be pretty much this, through the directional control valves, and then into the individual end user circuits for actuation. So we might cover a little bit of this toward the end of the class. I don't know what aircraft this was, but it did exist. I'm sure that they didn't just conjure this up out of something. But it came out of some aircraft. I kind of really wonder what it is. This is an unusual schematic too. It uses both variable displacement pumps and it uses constant displacement pumps too. We know that they've got constant displacement pumps because they use a pressure regulator in the circuit downstream of some of the pumps. But in this case, it looks like the left pumps eventually channel into a manifold that goes to the pressure regulator. But the right pumps do not. Those pumps were variable displacement, so the pumps will have a compensator in order to provide for control of discharge. And maybe this is kind of a strange landing gear deal as well. Some aircraft use hydraulic pressure in order to retain the gear in the up position. Other aircraft have mechanical up locks to hold them up. And but I don't know, this one also uses latch actuators that work that are single acting in order to hold the gear in the up position. When you apply hydraulic pressure, the spring compresses and then the gear is able to unlatch itself in order to be able to come down. But these have to be unlatched before the hydraulic pressure is used to bring the gear down. The main gear in this case, I think they've got integral, I can't remember if they've got integral down locks in them, but they're using hydraulic pressure to keep them retracted, and you get the latch actuator to hold it up. And we'll talk about this as well. For a lot of emergency brakes, they just separate the normal and the emergency system via a shuttle valve. So in the event that we don't have hydraulic pressure, for whatever reason, either we've lost fluid, we've got a reserve charge of air in a flask or a cylinder, and we'll meter that and make it available through the power brake control valves that are here. They use them as an alternate in order to move the shuttle over in order to make the brakes work. Normal actuation of brakes, they use a metering device. They call these power brake control valves, PDCVs. In the landing gear class, I think Lyle probably talks about these. We don't really have master cylinders in these types of brake systems. These meter main system fluid in order to provide for operation of the brakes, so they've got a metering function. When your feet are off of the brake pedal, it provides for interchange fluid out of the brake itself back to the return manifold. So that prevents a lock brake from occurring and prevents thermal expansion from actuating the brakes. But when you step on the pedal, you're cutting off the return and essentially metering hydraulic fluid under pressure that goes into the actuator of the brakes. Notice also too, one of the devices we talked about in class last week, here's a hydraulic fuse. There should be a normal volume or velocity of hydraulic fluid available to operate the brakes. If the quantity is exceeded, that indicates possibly a leak downstream of the valve. So what we'll do is we'll isolate the hydraulic fluid at this point. No more hydraulic fluid is available because the fuse has been closed. And then we're pretty much have to use whatever air charge is available in the storage flask in order to operate the brakes. Okay. And I don't know what else we can do. Here's an example of maybe some of the things we've talked about too in class tonight. This uses a rack and pinion type of actuator for a windshield wiper. The old Lockheed Electra, or at least Orion aircraft, the P3s, they used an actuator that used a pinion and a rack in order to make the windshield wipers work. The method of control for speed is pretty simple. What they do is they use a restrictor in order to control the flow. Can't see where that is. Switch, speed control unit. This is a restrictor. What it's doing is it's controlling the amount of fluid available in the line that ends up going into the actuators themselves, so it controls the speed. Even other military aircraft, like here's an S-2, this is a rotary type of master unit that routes fluid into actuators that are vanes that sweep back and forth, and it drives the blades to be able to sweep. They use a speed control unit. This is really nothing more than a variable restrictor in order to control flow. Notice also something too, like I mentioned in class, sometimes they'll install check valves in maybe a portion of the return manifold, or in many cases the return manifold, and that prevents back pressure from influencing operation of other components that are also similarly connected into the return manifold. So that's why they have them there. And I don't know what else to look at. Okay, anyway, you got an idea of some of the things we've kind of talked about tonight. Any questions on actuators and what they do? You know the difference, or at least the differences among single acting, double acting, and when we talk about balanced and unbalanced. You know a little bit about the disparity between forces and unbalanced actuators. You know the uses for different types of actuators. Usually single acting actuators are used for locks and latches, not too common. They require usually a three-way or a three-port selector valve. Double acting actuators usually require a four-port or a four-way selector valve for operation. Anything else? Can't think of much else that's important. Hydraulic motors, the necessity for them, provide rotational motion. The advantages of a hydraulic motor over an electric motor. You can stall a hydraulic motor without fear of a potential fire hazard. You know that. And the reason being is because the relief valve will open in the return manifold that will allow fluid to go back to the reservoir. So no harm, no foul. Electric motor, you immediately stop the armature, you'll cause arcing and sparking. So fire hazard potential. Another advantage too is quick start and quick stop. If with electric motors that drive any component, usually before you can reverse the motor operation, you have to completely stop it in the kit without, at least without damaging it. In the case of hydraulic motors, you can have instant reversal. It goes, just stops and then restarts in the new position. So really quick. All right, I guess I'm done. I'll see you out in the shop in a little bit. Make sure you turn your tonight.